Okay, so thank you, Steve, for inviting me to CPP. So it's a great pleasure to be here today and to see people again. So my talk is about verified compilation, where you have a software, the compiler, and a proof that the compiler does not introduce bugs. So among verified compiler, there is a CPP'23, a verified compiler for a functional language written and proved using whole, and there is CompCert, a compiler for the C language written and verified using CoC. So we started working on what would become CompCert almost 20 years ago. And in my talk, I would like to explain what we did to make CompCert a real compiler. I choose to focus on the semantics and the reasoning on the semantics, as they are the very core of the correctness proofs. First of all, I would like to thank Xavier Leroy, from whom I borrowed some slides from his lecture at Collège de France on verified compilation. So there is here a link to the slides if you are interested by the subject. So compilers are complicated programs. They may contain bugs. However, they have a rather simple end-to-end specification, which is as follows. The generated code must behave as prescribed by the semantics of the source program. So this specification is a property about semantics preservation. So it involves the semantics of the source and the target languages of the compiler. And the specification becomes mathematically precise as soon as we have formal semantics for the source language and the machine language. Then formal verification of the compiler can be considered. This idea of verifying in this way a compiler is not new at all. It was published 55 years ago in a visionary paper by McCarthy and Painter. In this paper, they explain how to compile a toy language with arithmetic expression into a small machine language where instructions are with stack instructions. 5 years later, Milner and Weyrauch mechanized this proof using the Stanford LCF prover. So today, this proof is taught to master students as an exercise. So in this exercise, you start by defining your source language. So you define arithmetic expressions. Then you define their semantics. Here, this is a recursive function called eval. It takes as input a state mapping variable to values. Then you do the same with the target language. So you define here a small stack language. So this language uses a stack to store intermediate results. And so you can push integer to this stack. You can load a variable from the stack, and you can perform arithmetic computations. So a program is a list of instructions, and the semantics of the program is here as well, described by a recursive function called exec. This function takes as input the state as eval, and also the stack to store the intermediate results. So initially, the stack is empty, and at the end of the program, the stack is made of the final value returned by the program. So let's suppose now that we have another function, the compiler. Here, this is a very simple compiler. It performs a single pass to translate arithmetic expressions into machine expressions. So once you have the semantics for your source and target language, once you have your compiler, so you can state the correctness of the compiler using a theorem such as this one. For all expression E, the value of the expression E, as given by the semantics of the source language, eval of E, is exactly the value computed by the compiled program, here using function exec. So this proof, so then you need to prove the theorem, and this is an interesting exercise because it's an opportunity to explain to students that sometimes you have you need more general theorem in order to reason by induction on a relation. So here you cannot prove directly this theorem. You need to generalize it in order to use induction hypothesis. So anyway, you do your proof, and then once you have done all this, you can extract your compiler, that is the OCaml code from the compiler that you can run outside of the proof assistant. And this is what is called the verified compiler. So in the second part, I would like to explain how to scale these ideas to the verification of real compiler such as CompCert. So CompCert was designed to compile critical embedded software. It's a moderately optimizing compiler. It targets several architectures: PowerPC, ARM, RISC-V, and x86. It is a shared infrastructure for ongoing research. There are several projects that are currently using CompCert. And CompCert is also a real compiler that is sold by the Absinthe company. CompCert has been used to compile critical embedded software in industry for avionics software and for nuclear power plant software. For the nuclear power plant software, the CompCert was also certified according to the associated standards. In both cases, the interest for CompCert stemmed from the fact that the people in industry needed to improve the performances of the generated code, and with CompCert they managed to do this while ensuring the traceability guarantees that are required by the certification standards. So CompCert accomplishes a series of 18 compiler passes, starting from CompCert C, the source language of the compiler, that has a non-deterministic evaluation of expression, down to assembly. So these compiler passes are standard compiler passes that you can find in compiler textbooks. For instance, there are optimizations such as constant propagation or common subexpression elimination. This optimization instantiates a generic data flow solver that is also part of a library in CompCert, and they operate over RTL for registered transfer language, an intermediate language where programs are represented by their control flow graphs. So each of these passes is proved correct according to the semantics of the involved languages. So there are 11 languages in CompCert, and each language has a formal semantics. So these semantics observe the behaviors of program. So a program may either terminate and yields a final value, or it may diverge if it executes an infinite loop, or a program may go wrong if it evaluates, for instance, a division by 0. So in this behavior, there is also a trace of external input-output events that is part of the behavior. And so there is in CompCert a generic library for describing full execution of program and their associated properties, given an abstract notion of small step semantics, a reduction semantics that reduce a semantic state S to a semantic state S prime, and that emits a trace T of external events. So from this step relation, here this is a relation and not a function as in the previous exercise. Anyway, you can describe the full execution of the program. And so a program may terminate in at least 0 step, or at least 1 step, or exactly in n steps. And a program diverges when there is an infinite sequence of steps in the execution. So in the following, I will write, given a language L, I will write exec L of P and B to mean that a program B has behavior, program P has behavior B. So let's suppose once again we have the semantics for the source and target programs on the one hand, and on the other hand we have a compiler function that describes all the 18 compiler passes for CompCert. So we can now state the correctness of the compiler using a theorems such as this one. For all source program S and compile code C, if we can compile S into C, and if S either terminates or diverges with behavior B, then C does exactly the same. So if S terminates, then C terminates with the same behavior, including the trace that is the same in both executions. So the standard proof technique used to prove this theorem is the use of simulation diagrams such as this one. So this diagram states that a step in the execution in the source program is simulated by steps of execution in the target program, while ensuring an invariance between source and target states. And moreover, in both execution on the source and target side, the trace of external event is exactly the same. So these simulation diagrams are compositional, meaning that we can chain them together to describe the full execution of a program. For instance, here, in the case of where a program terminates. But we also have diverging programs. So this is why we have chosen a small step semantics to better describe diverging programs. So we could be in the situation where the source program diverges, but the target program does not diverge. This would correspond to an incorrect optimization, but this situation could happen. And in order to avoid this situation, so where the source program stutters, so we have to strengthen the simulation diagram. And for instance, here we use a measure computed on source states. So this measure decreases during the execution of the source program. So this is here one of the simulation diagrams that is used to prove the correctness of some compiler passes. So here we have this. We have a simulation diagram that gives us a way to reason on the semantics. So this is the standard technique that we will use. And the difficult part in doing this proof is to finding the right invariance, because if you use simulation diagram, nothing helps you to write the adequate invariance. Moreover, another difficulty is that you have to find a measure for source states. So we have small step semantics, reduction semantics that we chose to model diverging executions. So their judgment can be read as follows. Given a statement I and a state S, I is reduced to I prime, thus updating the state S into S prime. So these semantics describe the dynamics of the program, and we also have a proof technique, the use of simulation diagrams. Simulation diagrams state that source transitions should correspond to target transitions, but target transitions are related to the target program that is statically compiled once for all. So we are in the situation where in the source semantics, some rules generate instructions that do not exist in the source program. For instance, to describe the execution of a loop whose condition evaluates to true, we unfold the loop. And so this generates the sequence body of the loop followed by the loop that is not, that it does not exist in the source program. Another example is the rule given here for the evaluation of an if statement whose condition evaluates to true. In the same way, these rules generate instructions that do not exist in the source program. So this is a problem because we need to make a correspondence between target instruction and source instruction. So this raises two issues when using simulation diagram. It's impractical to reason in the execution relation. More concretely, we can face situations where we cannot reuse directly induction principle generated by COP. And moreover, it may be difficult to define the measure because we do not have true reduction rules here. So the solution we found to this problem is to add continuations to the semantics. So we now have a new judgment that is as follows. Given an instruction, a continuation k and a state, an instruction I is reduced into I prime, thus modifying k into k prime and s into s prime. So a continuation here describes the remaining computation, including the structure of the instruction. For instance, we remember that we were in a sequence. So thanks to continuation, there is no generation of new instructions. So the reduced instruction is always a subterm of the initial instruction. And so, for instance, when we have an if statement whose condition evaluates to true, we now have a true reduction. The if is directly reduced into its then branch. So to deal with continuation, we need to add some rules in the semantics. So there are two kinds of rules. Focusing rules, for instance here, to execute a sequence of statements, we must explicitly say that we chose to focus first on the left of the sequence. This means that we reduce the sequence into its left part, and we push the second part into the continuation. And remember that we were in a sequence, hence the dot here. So the second family of rules are rules to resume the execution. For instance here, let's suppose that I have completely reduced my sequence of instructions. So the sequence is reduced into a skip statement, an empty statement. And then I need to resume, meaning that I need to pick up the next instruction in the continuation. So here we have the benefit of this is that now we have it's more easy to reason and to prove the simulation diagram, but we have added some more rules in the semantics, but they are easier to handle. So to sum up this second part, our goal is to prove a correctness theorem that is about small step semantics. The theorem is proved by reasoning using simulation diagrams. So this is a well-known and standard technique here. And to apply this technique to real languages such as C-like languages, we have defined semantics that observes behavior of programs, termination and divergence. Moreover, in the traces of external events is also part of the behavior. To use simulation diagrams, we had to strengthen them with anti-stuttering measure. And lastly, we had to design original semantics with continuation in order to facilitate the reasoning. So in the third part of my talk, I would like to present two independent and recent projects where we reused CompCert. In the first project to verify the preservation of a security property, and in the second project to verify the just-in-time compilation, so dynamic compilation. So let me introduce this first project. So the goal is to protect program against what is called timing and cache attacks. So these are side channel attacks. So where an attacker is observing the several executions of the same program in order to learn information on secret values that are hidden in the program. So in order to protect against these attacks, cryptographers used a programming discipline that is called cryptographic constant time. So the idea here is that the programmer should avoid to write programs where either condition or memory accesses depend on secret values. This means that the programmer is not allowed to write this program that has a condition that depends on the secret values. Of course, the programmer knows in advance what are the secret values. For instance, it can be a cryptographic key that the programmer wants to protect in his program. So instead of writing such a function, the cryptographer will use bitwise operators to avoid this branching on a secret values. So this is what is called a cryptographic constant time program. And there exist several tools that can check if a program follows this policy. So what we did is reusing and extending CompCert in order to ensure the preservation of this isConstant property. This means that we still have the compiler correctness theorem, and now we want a second theorem that can be read as follows for all source program and compiled programs C, if S can be compiled into C, and if S is cryptographic constant time, then so is C. So let's look more closely at this isConstant time property. So this property belongs to what is called a non-interference property, where you state that you may observe program leakages during their execution, and this observation does not reveal any information about secrets. So here, a leakage is either a Boolean guard or the value of a pointer used to access memory. So we reuse CompCert in the following way. So we enrich the CompCert traces of events with leakages, meaning that we have slightly updated the semantics to compute all the possible leakage among the semantic rules. So now we have two kinds of events in the trace. On the one hand, the external events of CompCert, plus the leakages that also belong to the trace of event. But we still have the same semantic judgment, meaning that we can reuse all what we had before, for instance, to describe the program execution. So this isCryptographic constant time property is what is called an indistinguishability property, meaning that it is related to two executions of a program, two different executions of the same program, contrary to the correctness property of CompCert that is related to only one execution of the source program. Here we need to consider two different executions of a source program in order to deduce that there is no difference between the generated traces. So more precisely, a program S is considered as being cryptographic constant time when given two indistinguishable states S1 and S'1. When we have the two corresponding executions, their traces are exactly the same. So two states are considered as indistinguishable when they differ, they share the public values, public meaning not secret, but they may differ on secret value. So the idea is to trigger two executions of a program and to see if they differ in the secret value. If the answer is yes, it means that the program is not cryptographic constant time. So this is the property we want to ensure here, and so it involves two executions of a source program. So maybe the most intuitive and the more general way of proving this property is as follows. So this is a theorem we need to prove. So our goal is to prove that the compiled program is cryptographic constant time, and so we need to consider two executions of this program. And so because we have two executions, so the intuitive idea is to say, okay, I need one simulation for each execution, but that's not enough because I also have indistinguishable states. So I also need to represent this relation. And then I have something that is much more complex than a simulation that is called a cube diagram. Moreover, here I need to define this invariance, and in the most general sense, I also need to compute precisely. I need to guess and to predict how many execution steps will happen in the target program. So this is the most general cube diagram we could have. So meaning that if we want to prove our property for CompCert, we need to have 18 such cube diagrams for all the compiler passes. We need to find the right diagrams, and we need to prove them. So this is very tricky. We first tried this approach and realized that it would be more complex than doing CompCert. So we changed our mind and decided to look for other ways of doing these proofs. So we had here a proof engineering problems because there is an existing CompCert. We want to reuse this proof. There are all these simulation techniques that are very useful. So can we leverage these existing proof techniques and the proof scripts as much as possible? The answer was yes, and this is what we have done. So we have a single semantics, but where traces consist of external events and leakages. But from this semantics, we can define an extraction in order to get either compile-only judgment, to get the same judgment we had with only CompCert, and on the other hand, the leak-only judgment, we need to prove the isConstant property. So what we did concerning the proof was as follows. So we started from the existing CompCert proofs. So what we have done is only slightly modifying the semantics in order to observe leakages. We didn't touch to the remaining CompCert. And we also had to generalize the simulation diagram a little bit. I will explain this on the next slide. But apart from this, we could reuse the existing proofs, meaning that in the existing proof, we only needed to fill some holes resulting from the fact that now we observe leakages. So this is the proofs we had to do. And then we had two more theorems, each one being a general theorem. The first one stating that the CompCert we have modified with the observation of leakages implies the CompCert we had before. But we prove this theorem only once because this theorem holds for any language of the compiler. So we only need to prove it once and not 11 times for each language. In the same way, we have a similar theorem that we proved only once, and that states that our slightly modified CompCert implies the proof we have done implies the proof of the is cryptographic constant time property. So in the end, we were able to reuse the simulation techniques of CompCert instead of these complex cube diagrams techniques. So let's look at an example where we had to generalize a simulation diagram. Indeed, our semantics observe leakages, and some compiler optimization may erase leakages. For instance, a leakage may be a condition, so an optimization may get rid of a condition. So we define what we call the leakage erasing simulations. A simulation, so an optimization that erases leakages still preserves cryptographic constant time as long as its decision to erase does not depend on secret values. And so we were able to generalize, to modify a little bit the simulation diagram in order to reflect this. So this is the new diagram we have for terminating programs. So here, the traces in the target execution is either the same as the traces in the source execution, but in the cases where the trace T in the source execution is a leak-only event, we may have an empty trace in the target execution. Moreover, we need to, in order to be able to use a simulation diagram, we must predict the number of steps that will be done at the target level. This means that we have a stronger invariant. We need to modify the invariants that are preserved. We need to do this prediction and to compute this and to put it in the invariant. And then what we will prove is the fact that the target program will execute in exactly n step this number that we had predicted before. So this is interesting because here we were able to reuse simulation diagram. We only had to modify them a little bit. And this is much better from a proof engineering point of view and for the difficulty of the proof than designing and proving a cubed simulation diagram. Now I'd like to say a few words about another recent project where we started verifying a JIT compiler, so a compiler that performs dynamic compilation. So this work was Aurel Barrière, the PhD thesis, and Aurel will give a talk at Popple on Wednesday on that topic. So here, roughly speaking, a JIT compiler interleaves the execution of a program with some optimization, some dynamic optimization. So initially, when you have a source program here, the JIT starts with interpreting this program. And then, among the components of the JIT, there is a profiler that tracks functions that are reused very often, or variables that may have constant values. And so, for instance here, after several calls of function f, maybe that the profiler will say, hey, this function is called very often. Let's try to optimize it. And let's optimize it dynamically, meaning that we will generate a new version for this function. So here, this means that we generate a new program. And for instance, here, a typical optimization is when the compiler speculates. For instance, it speculates that a value of a given variable will be constant. And so here, because of this speculation, we will have a specialized version for this speculation. But maybe that it was not a good idea to speculate. So we also need to be able to de-optimize to come back to the source program if speculation fails. So what we did is formally verifying a small JIT, a toy JIT, that specializes functions and speculates and de-optimizes. And interestingly here, we had to define a semantic new instruction for speculation and de-optimization. And their semantic is non-deterministic, as at any time, we may either de-optimize to the source program or continue to the next execution in the source program. So then we had to prove that JITed programs are equivalent to initial programs. So here is the snapshot of a possible execution of the JIT program. And we need to show that this execution is equivalent to the execution of the source program. So the idea here is to reuse the simulation techniques in order to prove this property. However, here we cannot apply this simulation such as this one directly, because here both the program and the execution state are evolving. In CompCert, so there is a single program, the source program. Here, the program changes, is evolving. So we cannot use directly simulation diagram. And so what we did is designing new simulations where this time we need to consider pairs made of a configuration and a program that are simulated. So pairs are simulated because the program is evolving as well. So Aurel managed to define an adequate simulation expressing this. And so we were able to reuse this simulation. So in this simulation, there is an invariant for JIT that can be explained as follows. At any point during the JIT execution, the current state CI corresponds to a source state, like we had before. But moreover, the current JIT program, PI, is equivalent to the source program, P0. So we could use a simulation to express this. And this simulation uses an invariant. And in this invariant, there is an equivalence between programs. And this equivalence itself is expressed using another simulation. So we call this nested simulations. So we need two simulations in order to prove the preservation to prove that the JIT program has the same semantics. But once again, we were able to reuse CompCert proofs and the simulation diagrams of CompCert. This was especially interesting here because the JIT compiler also reuses the backend of CompCert in order to generate more efficient code. So it reuses the optimizations of CompCert and so the simulation techniques. So to conclude, CompCert is a mature and fully verified compiler for C. We were able to reuse his simulation approach, which is very powerful and which we could adapt to other situations than just static compilations. So there are several reusable libraries in CompCert. So there is this general library for simulation, but there are other libraries. For instance, there is a memory model that is common to all the languages of the compiler that comes with many properties expected from a memory model that is also useful and could be reused outside of CompCert. So there are several projects today that use CompCert. Most of them are in compilation, so there are other verified compilers that rely on CompCert. For instance, their source language is different. So there is CompCert, where the goal is to verify probabilistic programs. There are compilers for synchronous languages, L2C and VELOS. And there is also VeriCert, that is a verified compiler that targets a different language. VeriCert targets Verilog. The idea here is to verify high-level synthesis. So currently in Rennes, where we work on CompCert SSA, a middle lane for CompCert where you have the SSA intermediate representation. So we started another project with the people from VeriCert, where we would like to reuse CompCert in order to verify high-level synthesis. So for that, we have extended CompCert SSA with a new intermediate representation that will be presented by Jan in the next talk in a few minutes. CompCert is also used, parts of CompCert were also reused to do static analysis. For instance, the Veresco abstract interpreters that reused the semantics of CompCert. And last, CompCert, the language of CompCert were also reused to define program logics. So VST in Princeton, Gillian in London, and Verifast in Belgium. So what I've presented is a joint work with many people that I would like to thank. And thank you for your attention.
Thank you. We have plenty of time for questions. Are there? Oh.
Sure. Since we have plenty of time, I'm going to try my luck with two questions on those last two projects you talked about.
Yep.
For the cryptographic constant time project, an interesting thing about the constant time property there is that it really forces programs to be quite simple, to the point where it's pretty feasible to just run static analysis on the machine code that comes out and not have to worry about anything about compilation. Did you think about that trade-off in deciding to invest in that project?
I don't think that doing static analysis on the compiled program is easy. And this is why we chose to do some static analysis, but on source program. We did this before proving the preservation of the source program.
Okay, we could talk offline.
Yeah,
I can try to make the case
yeah.
that's easy. And for the second project, isn't it the case that most JIT implementations are for significantly higher level or at least type-safe languages than C? I'm kind of curious what suite of optimizations you had available when program analysis is relatively hard to do to drive the classic optimizations.
Well, is JavaScript a type-safe language? Or?
Yeah, I think it must be much easier to understand JavaScript code for optimization than C code, where you don't have to worry about wild pointers and all the usual challenges of C code analysis.
Maybe we can discuss this
Okay.
as well.
A nice symmetry here. Thanks.
There was another.
You also mentioned the work on Verasco, which was about verified abstract interpretation.
Yes.
Is there any plans for the future use of this project, or is it going to go?
So we have reused Verasco to analyze programs in order to show that they are cryptographic constant time. So this was one project we did before verifying the preservation of constant time. And yeah, this project is over, and I don't know what Verasco will become.
There was one back here.
Thanks. So I was wondering, you mentioned for the JIT application that you're using a non-deterministic semantics.
Yes.
And also, if I recall, much of CompCert simulation infrastructure, including the theorem statement you showed, relied on a deterministic semantics, because you had the statement of like source behavior implies target behavior, which only makes sense if you have a deterministic source language. So I was wondering, like, well, how does it work together? What kind of challenges did you have when starting to use non-determinism in CompCert there?
So it works well because so I didn't show, there are several simulation diagrams in CompCert. I show one diagram. I didn't talk about forward simulation, backward simulation, non-determinism, and so on, but CompCert can handle non-deterministic semantics because the source language is non-deterministic. So the fact that the JIT has a non-deterministic semantic is not a problem, was not a problem for CompCert. It's not, the simulation we use is not what the one I've shown, but there was no problem with this. Yeah. If you want, we can discuss this offline.
First, thank you for the talk. One of the things that you have is you describe two extensions of CompCert. I suppose they are forks in the code.
Yeah.
So I have faced this with various other COC projects as well, where people just keep on making forks of the thing, and I find it very difficult to maintain. Do you have any thoughts on that? How would you see this, foresee this is going to work in the future? That there will be like 20 versions of CompCert for different things, they somehow come together, we need to improve tier improvers to better deal with these things. Do you have any thoughts on this?
My first thought is, so there is the real CompCert that is a compiler initially designed for critical embedded software and that is used in industry, right? And so the extension we did were not exactly about this related to this compilation. So, but on the other hand, what we learned from these two projects is that we could have more general simulations. And maybe it could be interesting. So I think that it would be interesting to have more general simulation diagram into CompCert, and maybe one day, yes, to integrate this in CompCert, but we are not ready yet to do this, I think.
But then concretely for the constant time version, you would have some flag in CompCert or so, and then you would hope to generalize all the simulation diagrams, and then depending on which flag of CompCert you get, either certain optimizations or some optimizations that you don't get, and then you hope to somehow factor out all the proofs.
Yeah, and what I didn't tell before is that when we started working on constant time, the first thing we did was to check that CompCert was fully constant time, and it was not. And now it is, because there is now a CMove instruction and so on. So what we did had an impact on CompCert that now preserves this constant time.
And these changes have been ported back into the original CompCert?
Yes.
Okay, so for the original CompCert is also constant time preserving.
Yes. Yeah.
But the proof of that is just in your work and not in the main CompCert repository.
Yeah.
Okay, I see. I have one other technical question. Can you go to slide 10, I think? The one where you have the correctness theorem, I think it's 10, it's one later.
This one?
Yes. I'm a bit surprised about the order of the implication in this theorem.
Yes.
Because of non-determinism,
Yes, I agree, but it's a simplified...
Oh, so this is the version for C Lite, not for CompCert C.
It's a simplified way of showing the theorem. But it is not exactly the theorem such as you are.
Okay, fair.
Yeah.
I think there was one more talk back here. Question.
Hi, I had a question that's a bit related to Robert's first question. So it's at some point, if I understood correctly, you had to modify the semantic as it was defined in CompCert originally.
Yes.
So you had to adapt many proofs. And I was wondering...
No, we added something in the semantics which resulted in new proofs.
So
we had to extend the proofs,
so
not to modify the existing proofs.
You never had to modify an existing proof?
No.
Okay.
More questions about this constant time stuff. So I mean, this seems like a hard problem, and in particular, just figuring out what, in the assembly counts as as a step that might reveal information seems difficult. So I'm wondering how you came up with those labels that say, this execution step reveals information about this piece of data. Did you just stare really hard at the semantics of the assembly, or did you ask experts, or like how did that happen, right? Because it could depend on the cache, it could depend on the pipelining.
So we knew precisely what were the leakages, pointers corresponding to memory accesses and so on. Thanks to the memory model, we were able to express this exactly where the leakages related to pointers. And so
Okay, so you felt like the existing memory model was like enough to know exactly what the
and of course we discussed with cryptographers, with practitioners to validate if what we did was meaningful for them. Yeah.
Okay. It was already standard definition. Okay. All right. Yeah. Thanks.
Any other questions? If not, let's thank Sandrine again.